Hello, data science students. I hope you're all doing well, staying happy, healthy, and safe. I'm assuming that you've all watched the Introduction to Image Analysis lecture that I posted earlier, and now we're going to be working on some code examples. As I've told you guys in class many times, you can edit your code using any IDE or editor or version of Python that will work for the purposes of your assignments. And for me, I like to work from a terminal. I'm in Windows 10 and I'm using Windows Subsystem for Linux, WSL. And so I've got two terminals open, and I keep these guys arranged so that they're kind of like they effectively serve as an IDE. I've got one side over here where I do my editing, and another side over here where I actually execute the code. So, you probably have a place on your computer where you store your source code, a scratch area, a source directory, a directory for your classes, something like that. Me personally, I have a source directory with a subdirectory called 343, specifically for the stuff that we're doing in this class. Whoopsie. There we go. And I've made a subdirectory in there called image that we're going to be working out of today. And let's go ahead and get both terminals in the same location. Okay. And I've also copied over some files, some images actually that I got from Creative Commons. Oh, and here's this guy. This is one of those. Pay no attention to the man behind the curtain. This is a remnant of a practice file I was working with earlier, so let's get rid of that. Okay, so now, nice clean directory. We've got some image files that I downloaded from Creative Commons. You can see their visual equivalents down here, just so we can reference those a little bit later. In case you want to reference these images, here's their image attribution from Creative Commons. Nice, cool, free images of 1960s MGBs. Matter of fact, we have a red MGB Roadster down here and a red MGB GT down here. I'm personally a fan of the Roadster, but if you watched the previous lecture, you've probably guessed that one already. Anyway, so let's start by editing some code. Let's make a file. I like to use the editor Emacs, but again, you guys can use anything you want. You can use Emacs, VI, Notepad++, Visual Studio Code, Eclipse, whatever. Just as long as it works for you and you know how to use it, I'm more than happy with any way you get this working. So let's make a file called image.py. So what's one of the first things that you do when you start writing your code? You import the libraries that you're going to be using. So today we're going to be working with NumPy. So we're going to import NumPy as np, and we're going to be displaying stuff using matplotlib. So we're going to import matplotlib.pyplot as mplot, and almost mplot. There we go. And we're going to be using a new library that we haven't used yet. And this is the Python image library. So depending on the installation of Python you're using, there could be a couple different ways to import it. A lot of you will just be able to do this. Import image, and it just works. So let's save this and run that code and see what we get. We're just importing libraries, so we really shouldn't see any output. This is mainly just a sanity check to make sure that our libraries are being imported properly. So let's see, Python 3 image.py. And uh-oh, no module image. Well, I followed the instructions on the class website for installing this, so it should be there. And this is where it gets a little bit tricky. If you get that message, that means you probably have to use a different line to import the image library. And you'll probably have to use this from PIL, so Python image library, import image. Okay, we can save that. We can run it again, and let's see what we get. Hey, no error messages, so everything imported properly. Sorta, maybe, kinda, probably, definitely did. Okay, so let's just do something simple. Let's show an image. Let's read in the picture of the red MGB Roadster. So we're going to need a variable to store image data in. Let's just call this img1. And to open it, we do img1 equal image.open. And we give it the name of the image file we want to open. mgb1.jpg. Okay. So that's fine. It's awesome. We've read in the image data. It's stored in the variable image1. How do we display it? Well, we're going to be displaying it using matplotlib like we do with all of our other assignments. And matplotlib has a function called imshow. And guess what? imshow stands for image show. So we give it one variable, and that variable is image1, image that we want to show. So let's save it. Go over here and execute our code, and nothing happens. Well, a common assumption that people make that's wrong is that imshow works like show does in matplotlib, and that it's for showing images. It is for showing images, but you also have to still call matplotlib show function. Okay, so let's save that and run it and see what we get. Ah, beautiful, beautiful. That's exactly what we need to see. Yeah, nice red 60s chrome bumper MGB. Yeah, that's a fine looking car there. Anyway, enough daydreaming, on with code. So in the previous lecture, I said that images are just numerical matrices, and you can treat them like that, and you can do math with these images just like you can anything else. And that is true. So let's prove it. So let's decrease the brightness of this image. Let's do image 1, let's decrease it by half. How would you decrease the brightness of the image by half? Well, you would divide your image by 2. So let's divide our image by 2.0, save it, and run our code. Oh no! Unsupported operand, divide equal for type JPEG image file and float. Darn it, Dr. Jones, lying to us left and right. Not really. It's true. As the image has currently been read in, we can't do mathematics with it because it's stored as byte data from the image file. But that byte data is just numerical values at each pixel location. So still a matrix, just in a different format. So before we can do mathematics with it, we have to convert our image matrix into a format that we can actually do math with. So a bunch of different ways to approach this. The way that I recommend is using NumPy to convert your image byte data into something like an array of floats. So let's do image1 equal mp.float64, and then give it image1 as an input parameter. So what this is going to do is going to take that byte data that we read in from mgb1.jpg and convert it to floating point values, things that we can do numerical operations on, things that we can do math with. Okay, so let's save that, and let's run our code and see what happens. Hey, that doesn't look right. That is very, very, very curious. Why does it look that way? Well, what did we just do? We just took our beautiful image byte data and turned it into something else so that we could do math with it, which means it's not byte data like we got read from our image file anymore, which means we have to convert it back before we show it. Now, one of the things I do want to point out, let's open that back up again, is notice we can still see that some parts of the image are still there. Things just don't look right, and it's because they're not in the proper format. They're still numerically changing on some range from 0 to something else, but it doesn't match the expected data format for displaying an image. So let's fix that. So NumPy can be used to convert it back. But now here's the thing. There is no NumPy conversion to JPEG format. So we've got to think about how that data was numerically stored in the image file. And how it's stored is as an unsigned 8-bit integer. So an 8-bit integer gives us a series of values from 0 to 255. And most image formats are on the range of 0 to 255. And 8-bit integer is 1 byte. So it's an integer value with a size of 1 byte ranging from 0 to 255. And how we do that conversion now is we set image1 equal to numpy uint8. pass image1 in as a parameter and save that. And let's run our code and see what we get. Hey, now that looks good. That looks like a half as bright image. So the MGB on a cloudy day, so to speak. So not bad, not bad. But now that's neat. You know, we can modify an image. But what we want to do is we want to do mathematics using multiple images. Because your upcoming assignment is to take in a bunch of images, compute an average image, and then compute a standard deviation image. So how are we going to read in multiple images? Well, for your assignment, you're going to have to do it probably with a for loop and read in a series of images. For the purposes of our example here, to get your ball rolling, we're going to read these in line by line. So let's make a separate image variable here. We'll call it image2, and do image2 equal image.open, and we're going to open mgb2.jpg. Okay. Now let's play around here. Instead of having that, let's make it a third image. We'll call it image3, and let's let it be the sum of image1 and image2. Okay, so let's save that and see what happens. Oh no, something went wrong. Okay, so it's giving us an error, and the error says operand could not be broadcast together with shapes 634, 976, 3, 682, 1024, 3. That is a weird error. Well, here's what this error means. It's telling us that our matrices that we're trying to do math with aren't the same size. So remember from our previous lecture that I said when you do mathematics with matrices, they have to be of the same dimensions. And in terms of images, that means they need to be the same resolution. So one image is smaller than another image. So what we're going to have to do is resize our images so that they're the same size, so we can do mathematics with them. What I recommend doing is actually downsampling to the smaller image. So if you upscale the small image to the resolution of the larger image, you actually lose detail in the smaller image, and it gets blurry and stretched out, and so you could get some erroneous information. However, you do lose image information when you compress it, but it doesn't get blurred out. It usually gets compressed down into smaller areas. And you will lose information, but you won't have any blurring out like you would if you stretch this up to a larger resolution. So I actually recommend that you downscale your larger image to the resolution of your smaller image when doing your mathematics. Is this going to be the best way to approach it for every time you got to do image analysis? Definitely not. But for the example we're working with today, this is my recommendation. For your assignment, though, each of your sets of images are going to be coming from a single webcam, so they're already going to be in the same format. The only caveat is that the images in your data set, some of them will be corrupted, so you'll have to filter those out. You can either do it by hand or programmatically or whatever. But that is a talk for another day. Let's see. Matter of fact, that's a talk for our live class. So if you have questions about that, hold on to them and ask them so everybody can hear it. Okay, so what do we need to do to get these guys resized? So let's see what we can do. First, let's figure out which one of these is which. A couple ways we could go about it. One way is we could resize our images, arbitrarily. Not arbitrarily. We could just go ahead and resize both of them down to the smallest resolution. That's one way to go, but a better way to go would be to just scale down the images that need to be scaled down. So let's see, let's do print and image1.size. Let's see what we get. Matter of fact, let's go ahead and comment out this code here so that we don't have to execute it. and run this and see what we get. Okay, so one of the things you'll notice is that it gave the resolution with the larger number first. This is given in horizontal and vertical. Now this up here, when it was giving this, we were getting our vertical, horizontal, and our depth. So remember in our previous lecture, we talked about there being 3 subpixels to every pixel. You don't have to think about that when we're doing our math, but yeah, that's what that 3 is there's a red, green, and a blue component. So when we're working with resizing our images, our horizontal resolution is first, and our vertical resolution is second. So this looks like it is our smaller of the two. So that means we need to resize our second image down to the size of our first image. Okay, let's get rid of our commented out code, or rather our comment block there, and set image2 equal to image2 dot resize. And let's see, our horizontal resolution was 976, and our vertical resolution was 634. Okay, let's save that and run our code, and oh my goodness, it broke! So if you get an error that looks like this, the reason you're seeing that is because it makes sense to give this 2 parameters, right? Horizontal resolution and a vertical resolution to resize to. Well, it's expecting that in a list. So it's actually expecting the first parameter given to resize to be a list of resolution, so X resolution and Y resolution. And you can add additional parameters there that, what these are, telling it which filter to use for your resampling. If you take our graphics class, we'll talk about that, but for the purposes of this assignment, you don't have to use any of these. Just leaving all the parameters blank after you enter your horizontal and vertical resolution is going to be fine. Okay, so let's save this. Let's clear our screen here and execute our code. Okay, so stuff broke. That's okay, but we didn't get the same error message that we got before. Now, this is the easy, hard-codey way to do an image resize from one image to the next, or so that one will match the resolution of the other image. The better way to do this, and it doesn't matter to me which way you end up using, is you can also do image2 equal image2 dot resize, and instead of hard coding the resolution, you can do image1 dot size, and it'll do exactly the same thing. This way, if you ever swap out your images, it'll always use the resolution of image 1. And so if we execute it, we get the same thing we're having before. Now, one of the things that you'll notice is we do have a bug down here. In IMShow, we're still showing image 1 instead of image 3. And how did we fix that problem with image 1 before? It had to do with the type of data that we had stored in our image. And so we've converted it to float 64. And we need it as an unsigned 8-bit integer. So we can do image3 equal np.uint8 and image3. And we'll convert this down here, or set that in IMShow from image 1 to image 3. And let's see what we get. Whoa, something weird. That's wild. That's not what we expected to see. Huh. Well, part of that might be a result of us not converting image 2 into a float 64. So let's see if that happens to be part of our problem. So image 1 equal, or image 2 equal mp dot float 64 image 2. Okay, let's save that and run our code and see what happens. No, no, we still would have had problems, but that's not the problem that we're seeing right here. Now, I alluded to something when we were talking about doing mathematics with images and displaying the results in our previous lecture. And that was, you can do mathematics with pixels and get really large pixel values beyond 255. You can do mathematics with your images and get values below 0, but those don't make sense when you try to display them. So let's see if we can figure out what our problem is. It may be that when we're adding these two images together, matter of fact, let's look at our output again and put it over here near our two source images. Now if we look at the areas of the images that are dark, where they overlap, everything actually kind of looks alright. But these bright areas, like where the sun's shining through the trees, things seem to be going wonky. And here where the hood is nice and bright here and the hood's nice and bright here, the colors are just wrong. And that's because the pixel values at those locations are adding up to be greater than 255. So pixel values typically have to be from 0 to 255. That's an 8-bit integer. So what do we need to do here to make this appear properly when we're doing IMShow is we need to clip our values such that they fit in the range of 0 to 255. And there's a function built into to our NumPy float64 matrix here called clip. So you can do image.clip 0 to 255. And any values that are lower than 0 will be clipped to 0, and any values that are greater than 255 will be clipped to 255. So let's run our code and see what we get. Okay, cool. Now that actually looks like those two images added together. Now keep in mind, this is the two images added together, not averaged together. So if we wanted to actually average these images together, we're most of the way there. So we're just adding two images together. If we wanted to make this an average image of image 1 and image 2, what would we need to do? We would need to divide our image 3 by the total number of images added together in image 3. And that's, in this case, that's just 2, image 1 and image 2. So we can divide that by 2.0, save our code, and run our script. Hey, there we go. Now it's not a hugely washed out image. It actually looks very similar to what we'd expect if we averaged these two pictures together. So, kind of neat, kind of neat. This same principle is what you're going to need to apply to each of the steps of your next project. So, like I mentioned, you're going to be doing an average image, and then you're going to be doing a standard deviation image, and then highlighting areas of high change for a given threshold in your resulting image. And so even though this looks, super simple, this is the basics you're going to need to know and understand to get your next assignment working. So play with this code. Go download your own images, do things other than, calculating the average of two images. Maybe try to write a for loop that reads in some number of images and calculates the average or whatnot. And that'll be a good place for you to get practice working with images in Python and prepare you for your next assignment. Okay, so there's our code examples for today. If you have any questions, please get in touch with me, get in touch with Riley. We're happy to talk with you guys and help you out. And otherwise, I hope you're all staying happy, healthy, and safe. Take care, folks. Hello, data science students. We just saw each other virtually writing code. But I wanted to take a minute to go ahead and tell you, be sure to look at the source code that I'm posting to Blackboard. It's the source code that we went over today, the stuff that we wrote, plus one little addition, one little extra special addition that's going to help you out in your next assignment. Matter of fact, I've highlighted it in yellow to draw your attention to it. So please, when you work through these examples, start with the source code that I've posted to Blackboard. And if you have any questions, ask me, ask the TA. We're here to help, and we're hoping you're all staying happy, healthy, and safe. And see you in cyberspace, folks. Bye-bye.